Hello folks and welcome back. Today we're going to be jumping into section 8.3 here, which covers graphing rational functions. Now we're going to split this up over 2 days, but today is going to be the first bit that we go over. Now to start thinking, we have a couple of graphs here. We're going to look at these graphs and the equations underneath. So this graph corresponds to this equation. Then we're going to try to figure out what parts of the graphs, for example, asymptotes, y-intercepts, and holes, can be explained by the equations. So to start off, we have this first one. We have this nice little curved loop in here. And the equation is x squared over x squared plus 1. So if we're looking at this, we see we have x squared plus 1, so we're saying we have no vertical asymptote. We have no vertical asymptote here. We have no vertical asymptote. The denominator never equals 0. What does that mean? That means that our graph will be continuous. Right? Our denominator never equals 0, so we're not going to have any sort of discontinuities, any sort of random jumps. So this is going to be something we call continuous. Okay, what about this next graph? This graph just looks like a line. We have a y-intercept and we have a line here with a slope of 1. So this appears to be the line y is equal to x plus 3. Except for we have some sort of issue with an open hole right here. Let's look at the equation, see what that tells us. We have y is equal to x plus 3 times x plus 2 divided by x plus 2. Now this looks not very similar, but if we cancel these out, we see that this is y is equal to x plus 3. Unfortunately, we can't just cancel that out because when we look at this bottom, we need to make sure it's never equal to 0. So what number would make the bottom 0? That would be negative 2. So we know x can't be negative 2. Right? So we know x can't be negative 2. We have something we call a hole there, because this looks like y is equal to x plus 3 everywhere except x is equal to 2. So this is going to be y is equal to x plus 3 everywhere except x is equal to 2. Okay, what about this final one? Looks like we have a horizontal asymptote here at 1, and we have a vertical asymptote here at 2. Okay, well, looking at this equation, we have x plus 4 over x minus 2. Remember, we never want the denominator of our equation to equal 0. So what would cause this to equal 0? That would be x is equal to 2. So we know x can't equal 2, and that has to do with our vertical asymptote here. Now, as I said, today we're going to be dealing with rational functions. So let's start off with some definitions. For starters, what's a rational function? Rational function is any function that can be written in the form of p of x over q of x. So essentially, anytime we have x's in both the numerator and the denominator, especially when those are polynomials, but we need q of x not to equal 0. Right? We can never divide by 0, so we have to make sure q of x isn't equal to 0. Okay, what about a continuous graph? What does it mean to have a continuous graph? It means we have a graph with no holes, no jumps, or no breaks. No holes, jumps, or breaks. What this means is that if you were trying to draw the graph on a piece of graph paper, you could draw it all in a single line. Going back up to these examples, we could draw this first one in a single line without lifting up our pencil. Right? We could do it the entire way across. But with this one over on the left-hand side here, or on the right-hand side, we would have to start by drawing this part, we'd have to lift up our pencil and start drawing the second part. So that would not be continuous. This one in the middle would also not be continuous. Those would be what we call discontinuous. A discontinuous graph is a graph with holes, or jumps, or breaks. Or in other words, it's a graph where we do have to lift our pencil when we're trying to graph it. So think about drawing the graph on a piece of paper and whether you could do it all in one single pencil stroke or whether you'd have to lift up your pencil to explain it. Now we're going to discuss some of the parts of a graph of a rational function. We're going to look at three in particular. We have holes, vertical asymptotes, and horizontal asymptotes. Holes are what we also call removable discontinuities. We will have a hole in the graph, we will have a removable discontinuity if there's a factor in the numerator and denominator that cancels. So if there's a factor in the numerator and denominator that cancels. For example, let's take a look at this problem we have down here. We have x minus 1 times x plus 4 over x minus 1. Now we have an x minus 1 in both the top and the bottom. Those are going to cancel, but we're going to leave a hole there. Just because they cancel doesn't mean that we can actually cancel them, because we need to make sure our denominator is not equal to 0. What that means is that this graph will look like y is equal to x plus 4, but we're going to have a removable discontinuity, or a hole in the graph, where the bottom is equal to 0. So it's x plus 4, but with a hole when x is equal to 1, because that makes it our denominator 0. So that's a hole. What about vertical asymptotes? We will have vertical asymptotes when there's a factor in the denominator that won't cancel. So essentially, if we can cancel it, we're left with a hole, but if we can't, we're going to get one of those giant leaping jumps and bounds. So there's a factor in the denominator that can't cancel. Like, for example, if we have this equation here, y is equal to 3 over x minus 3, we have nothing to cancel x minus 3 for. That means that if we put in x is equal to 3, we'd be trying to divide by 0. That can't happen, so we're going to have a vertical asymptote at x is equal to 3. And our last one here is the most confusing. It's called horizontal asymptotes. These are the ones where we get close to the lines going in y, but they never touch. So if we have p over q, right, this is our rational function, we have something on the top divided by something on the bottom. The horizontal asymptote depends on the degree of each polynomial. If we call the one polynomial on the top, if we call that degree m, and the one for q, n, then if our degree on the top is less than our degree on the bottom, we will have a horizontal asymptote at y is equal to 0. So if our degree on the top is smaller than our degree on the bottom, we'll have a horizontal asymptote at y is equal to 0. Or in other words, we'll have a horizontal asymptote at the x-axis. Let's take a look at an example of what that means. Okay, here we are with our graphing calculators. Now our first little bit here said that if our degree on the bottom was less than our degree on the top, or degree on the top was less than our degree on the bottom, then we'd have a horizontal asymptote at y is equal to 0. We would have lines that approach y is equal to 0 but never touch. So let's take a look at our graph here. Our degree in the top is 1, our degree in the numerator is 1, our degree in the denominator is 2. So if we have a degree of 2 here, it's smaller, or it's larger on the bottom than it is in the top. Let's take a look at the graph. Now as we see, our graph has points that get close to y is equal to 0, but as we go out towards infinity either way, they never touch. That's what it means when it says that our degree will determine that we have a y, or a horizontal asymptote at y is equal to 0. Now what about the other way? What if our degree in the top is larger than our degree in the bottom? If that's true, we will have no horizontal asymptotes. So if we have a degree larger in the top than in the bottom, we'll have no horizontal asymptote. Let's see what that looks like on a graph. Okay, so here we are. Our degree in the top is a square, so it's 2. Our degree in the bottom is 1. So our degree in the top is larger than our degree in the bottom. We expect no horizontal asymptote. Let's see what we get. It looks like, as we're doing this, we swoop in, but we don't have a horizontal asymptote. Don't have any point that y doesn't approach. Instead, it looks like we might have a line that it gets close to, but you'll deal with that more in pre-calculus. The last one is the trickiest. If our degree in the top and bottom is the same, then what we're going to have is we're going to have a horizontal asymptote at y is equal to a over b, which isn't helpful. What is a and b? A is going to be your leading term coefficient for your numerator. So a is going to be the largest term coefficient for your numerator, leading term coefficient, for your numerator, and b is going to be your leading term coefficient for the denominator. So essentially, when you have degrees of the same value, you're going to take the coefficient for your largest term in the top and divide it by the coefficient for your largest term in the bottom. So b is going to be the leading term coefficient for the denominator. That one's a little bit confusing, so let's take a look and figure out what that means. We're going to look at a graph here. Here we are back with a graph. What is our degree on the top and the bottom? They're both squared. So that means both of our degrees are the same. If we have them being the same, then we expect our horizontal asymptote at a over b, at the leading term of the top divided by the leading term of the bottom. So what does that mean? We expect our term to be at 4 divided by 2. We have 4x squared divided by 2x squared. We're going to be at 4 over 2, or 2. Let's see if that's where our horizontal asymptote shows up. So looking at this, looks like we do have a horizontal asymptote at a line we can't cross right through the center here at 2. Okay, so those are our different definitions here, the different parts that we're going to be looking for. Make sure you have this table down because we're going to be using it as common knowledge here in just a second. So make sure you have this to refer back to. Okay, once you have these all down, we're going to move on. Now we're going to look for holes and asymptotes, both vertical and horizontal. So asymptotes and points of discontinuities, or holes, in each of these. How do we do that? Well, what we're going to need to do is we're going to need to factor all of our terms. So we're going to need to factor everything first. Let's start off with this first one. We have y is equal to x plus 3 over x squared minus 4x plus 3. What does this make when factored? Well, we'll have y is equal to x plus 3 is factored on the top. In the bottom, we're looking for factors of 3 that add up to negative 4. It's going to be negative 1 and negative 3. So what does this mean? It means that this is our factored form. This tells us that we're going to have vertical asymptotes because we can cancel nothing out. We're going to have vertical asymptotes where the bottom would equal 0. So where would our vertical asymptotes be? Well, if 1 was x, we'd have a 0 in this first term. So we're going to have a vertical asymptote at x is equal to 1 and a vertical asymptote at x is equal to 3. Substitute in 3, this second term becomes 0. Any points of discontinuity? Any holes? No, because we have no terms that we can cancel. The last thing we need are the horizontal asymptotes. How do we determine horizontal asymptotes? We'll look at the degree in the top and the bottom. So the degree in the top is smaller than the degree in the bottom. Our table tells us for degree in the bottom is larger than our degree in the top, we have a horizontal asymptote at y is equal to 0. So let's put that in. We have a horizontal asymptote at y is equal to 0. And just for this first one, let's do a quick check and make sure all of this looks correct on a graphing calculator. Right, we've put this into a calculator. We have x plus 3 over x squared minus 4x plus 3. We expect vertical asymptotes at 1 and 3 and a horizontal asymptote at 0. Let's see if that's what we get. Looks like we do have a point where x can't go at 1. Looks like we have a point x can't go at 3. And it looks like our graph gets closer and closer to 0 on both sides. So that's exactly what we expected from that. We're good to go. Let's try a couple more here. Next we have x squared minus 4x plus 3 over x minus 4. First step's going to be to factor this. What are the factors of x squared minus 4x plus 3? We're looking for factors of 3 that add up to negative 4. It's going to give us x minus 1 over x minus 3. And then x minus 4 on the bottom is just the same. Okay, what about holes? Anything we can cancel out? No. So we move on to vertical asymptotes. Vertical asymptotes happen where the bottom would equal 0, and x being 4 would make the bottom equal to 0. So that's our vertical asymptote. What about horizontal asymptotes? Well, our degree in the top was 2, our degree in the bottom was 1. Being as our degree in the top was greater than our degree in the bottom, looking back at our table, that tells us we have no horizontal asymptotes. Okay, what about 3 here? We have y is equal to 2x over 1x plus 3. Remember, we have that hidden 1 out there. So nothing we need to factor. All we need to do is look for our vertical and horizontal asymptotes. What's our vertical asymptote? What makes this bottom equal to 0? Well, it would be negative 3. So we're going to have a vertical asymptote at negative 3. What about a horizontal asymptote? A horizontal asymptote will happen. See, our degrees are 1 and 1. So that means we have to divide the biggest terms of x together. So our horizontal asymptote will be 2x over 1x. Or cancel out those x's, it's going to be 2 over 1. So our horizontal asymptote is y is equal to 2. All right, we're going to skip 4. We're going to move on to 5. Then we'll have you all try some on your own. For 5, we have x squared plus 2x minus 3 over x minus 2. What does that look like factored? Well, factors of negative 3 that add up to 2 are going to be x plus 3 and x minus 1. Right, instead of doing our ACB chart, we're just looking for those factors and shortcutting them in. In the bottom, we have the same thing, x minus 2. So looking at that, vertical asymptotes are going to be what makes the denominator 0. What makes it 0 is x is equal to 2. What about holes? Well, we have nothing to cancel out, so we have no holes. Last, we have horizontal asymptotes. Remember, those depend on our degree in the top and bottom. What's our degree in the top? It's 2. Our degree in the bottom is 1. So look back to your tables. Degree in the top bigger than the degree in the bottom tells you we'll have no horizontal asymptotes. Right, there's some examples for you. Let's have you all try a couple. Doing the same thing, determining the asymptotes and points of discontinuity. Remember to start off by factoring. So looking at this first problem, we have y is equal to x plus 1 over x squared plus 5x plus 6. To start off with, what would this look like factored? So to factor this, we need to take this. X plus 1 is going to be good. We don't need to factor that. But for the bottom, we're looking for factors of 6 that add up to 5. We're going to get x plus 2 times x plus 3. So this is our factored form. Does this tell us that we have any holes? The answer is no, because we have nothing to cancel out. Okay, what about vertical asymptotes? Where do we have vertical asymptotes? Vertical asymptotes happen where the denominator equals 0. So what would make the denominator equal to 0? negative 2 would. It would make our first term equal to 0. And negative 3 would. It would make our second term equal to 0. So we have vertical asymptotes at x is equal to negative 2 and negative 3. Okay, what about horizontal asymptotes? Where is our horizontal asymptote going to be? Remember, your horizontal asymptote depends on your degree in the top and bottom. The degree in the top is 1, the degree in the bottom is 2. So our degree in the bottom is bigger. Go back to your table, see what that tells you. If your degree in the bottom is bigger, it tells you you have a horizontal asymptote at y is equal to 0. Right. Let's have you do this second one. We have problem 2 here. It says x squared minus 4 over x plus 2. To start off with, what is this going to be factored? To factor this, we're going to need to get factors of negative 4 that add up to 0. Right? X squared minus 4. That's going to leave us with x plus 2 times x minus 2 in the top. And in the bottom, we're going to have x plus 2. Now to start off with, do we have any wholes? The answer is yes. We have a term here, x plus 2, that shows up in both the numerator and denominator. So we can cancel those out, but not before saying we have a whole at that value, the value that would make this 0. So we're going to have a whole at x is equal to negative 2. Remember, even though you can cancel this out, you need to look for where the bottom would be equal to 0, and you'll still have a whole there. So the answer for this problem is it's actually going to be y is equal to whatever remains, so x minus 2, except for we have a whole at the point that would make our denominator 0. Okay, problem 3, we have y is equal to 3x over negative x plus 4. What is the factored form of this? Factored form, we don't need to factor anything on the top, that'll be 3x. And then on the bottom, you can factor out a negative, but it's not necessary. So you can write the bottom as negative x plus 4, or you could write it as negative x minus 4. Pull out the negative, either way, that will work. Okay. Do we have any wholes? Do we have anything we can cancel out in the top and bottom? No. So we move on to vertical asymptotes. Where's the vertical asymptote going to be? The vertical asymptote will be whatever makes the denominator 0. So what makes it 0 is if x is 4. Right? If x is 4, we'll get negative 4 plus 4, or we'll get 0. What about our horizontal asymptote? Where will that be? Horizontal asymptote depends on the degree in top and bottom. Since our degree is the same, it's both 1 and 1, 3x and x, our horizontal asymptote will be at the coefficients divided. So we have 3, and we're going to be dividing it by our coefficient for x is negative 1. So in other words, our horizontal asymptote will be at negative 3. Just 2 more of these. Starting with this first one, y is equal to 3x squared over 4x minus 1. What is this going to be factored? That's a trick question. We don't need to factor this. So we'll leave this as y is equal to 3x squared over 4x minus 1. Now what about vertical asymptotes? Where's the vertical asymptote going to be? Vertical asymptote causes the denominator to equal 0. So that's going to be at x is equal to 1/4. Substitute in 1/4 into the denominator, and we get that the denominator is equal to 0. How do we find its 1/4? Well, we can set 4x plus 1 equal to 0, and then figure out what x causes that to equal 0. Okay, what about horizontal asymptotes? Horizontal asymptotes depend on our degree. So we have 3x squared over 4x. Our degree in the top is bigger than our degree in the bottom. Top bigger than bottom means we have no horizontal asymptotes. All right, one final one here. We have y is equal to x minus 1 over x squared plus 2x minus 3. What's this factored? Top remains not factored, so we leave it as x minus 1. Then we're looking for factors of negative 3 that add up to 2. That's going to give us x plus 3 and x minus 1. Vertical asymptotes are going to be what? Vertical asymptotes are going to be what causes this to equal 0. So if we substitute in a negative 3 for x, the denominator equals 0. We have negative 3 plus 3 in the bottom. If we substitute in 1 for x, we'll get 1 minus 1, so our denominator will equal 0 as well. And finally, what about horizontal asymptotes? Horizontal asymptotes depend on our degree. We have a degree of 1 in the top and a degree of 2 in the bottom. Our degree being larger in the bottom, look at your table, it tells you that we're going to have a horizontal asymptote at y is equal to 0. And folks, that's all we're covering for this lesson today. We'll come back and cover a little bit more, but for now, make sure you're comfortable with those vertical asymptotes, those horizontal asymptotes, and those holes.